Hello and welcome. Do you know what a dentist gets for their first year work anniversary? A little plaque. And that's exactly what we're going to deserve after we finish this next topic, related rates. Let's turn over to the notes and see what we've got. As an introduction to related rates, consider a square that's increasing in size over time. And I've already drawn a picture of a square with sides 1, a square with sides 2, and a square with sides 3. So let's just suppose that after 1 second the square has sides 1, after 2 seconds the square sides grow in length to 2, and at 3 seconds they grow in length to a side of 3. Well, the areas are changing as these sides are changing, or in other words, the areas are changing as time is changing, right? The area of the first square would be 1 square unit. The area of the second square would be 4 square units, and then 9 square units. Notice that the areas are changing at a faster rate than the sides are changing at. So each unit of time, the sides only increase by 1, let's say, but the areas are increasing much faster than 1. So what exactly is this relationship between these two rates, between the rate at which area is changing with respect to time and the rate at which the sides are changing with respect to time? One way we can write these rates are using derivatives, right? dA dt would represent the rate at which the area function is changing with respect to time, dA dt. The rate at which the sides are changing with respect to time would be dx dt. dx dt, the rate at which the sides x are changing with respect to time. Well, to get at this relationship between these two rates, we can start by knowing that the area of each of these squares is x squared, right? You take the side of the square, you square it, that's the area. And if we differentiate both sides of that equation, a equals x squared, with respect to time, which we're using t for time, then here's what we get. Let's first write out what we're doing. So we're differentiating both sides of the area formula, both sides of that equation, with respect to time. Notice that area is a function of time. Area is changing as time is changing, so somehow it's a function of time. Notice that x is also a function of time, because as time changes, the variable x is changing. In our example, it was increasing by 1 every second. So in both of these cases, both of these derivatives, because the variable that we have here is different from the variable we're differentiating with respect to, we're going to have to use implicit differentiation. And that's one of the reasons why we cover implicit differentiation right before this packet. Now, on the first thing we're going to do is the derivative of area with respect to time. That's going to just be dA dt. There's another way of writing that. And then on the right side, we're going to have to use a chain rule because we've got the x function inside of the squaring function. Remember, x is some kind of function of t, right? It's a function of time, and that's inside of the squaring function. So we'll take the derivative of the outer, so multiply the 2 in the front, subtract 1 from the exponent, and we're going to leave that inner function, which in this case is x, we're going to leave that alone. But then we've got to multiply by the derivative of the inside with respect to t. Most of the time when we took derivatives, we took the derivative with respect to x. But here, we're taking it with respect to t because we want to know, we want to be looking at the rates with respect to time. We want to see what is the number of meters per second that the side lengths are increasing. That's dx dt. So this equation that we just got gives us the relationship between those two rates, between the rate at which area is changing with respect to time and the rate at which the sides are changing with respect to time. The equation gives us that relationship between these two. So we can use that relationship to answer questions like how fast is the area changing when the sides have length 5 meters. That would be x equals 5. So this is x. And are changing at a rate of 1 meter per second. In other words, dx dt is 1 meter per second. So we can use that relationship to find that out because we just take it and plug in x equals 5 and dx dt equals 1. And you get 2 times, so following the 2x dx dt, we have 2 times x, which is 5, times dx dt, which is 1, and we get 10. And now we're going to want to write the units for this. This is a rate, so it's going to be 10 something per something. And actually the derivative gives us the clues as to what the something per something is going to be. It's going to be units of area, which in this case, since the length is in meters, area will be in square meters. And then per units of time, which if we look down here at the 1 meter per second, that's the clue that time is measured in seconds. So it's going to be 10 square meters per second. So that's how fast the area is changing when the sides have length 5 meters and are changing at a rate of 1 meter per second. One thing to notice is that we need both of those conditions in order to figure out how the area is changing with respect to time. Just knowing that the sides are changing at a rate of 1 meter per second doesn't say exactly by itself how fast the area is changing. Because as the sides grow in length, the rate at which the area is increasing is increasing. It's growing, the areas are growing faster as the side lengths are getting bigger. So the rate at which the area is changing with respect to time not only depends on the rate at which the sides are changing, but also depends on the side length at that particular point in time. Okay, that's just an introduction into a related rates situation. Let's get into a more meaty example, as they say. Example 1 says that air is being pumped into a spherical balloon, so ball-shaped balloon, so that the volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Let's draw a picture of a sphere first. Ooh, not bad. Wow. I hope I don't have to fix this recording for any reason. That was a nice circle, which now is going to be turned into a sphere. Yes. Feeling good. All right. We're going to draw the radius of the sphere. We'll call that r. And just to be nice, I'm going to start labeling the variables that we're going to want. So I'm going to write v is talking about the volume of the balloon, and r is the radius of the balloon. The radius is understood just by the picture, but I'm going to be nice and write everything out. The reason we're including a volume as a variable is because we're given the rate at which the volume is increasing. It's 100 cubic centimeters per second. So we need a variable to talk about volume so that we can then write that this 100 cubic meters per second is the rate at which volume is changing with respect to time. In other words, dv dt is 100. And this is in cubic centimeters per second. So there's dv dt, is 100 cubic centimeters per second. Now, one thing to write down that's important is what we're looking for. So we're looking for how fast is the radius of the balloon increasing? how fast is the radius of the balloon increasing? In other words, our goal is to find, the rate at which radius is increasing with respect to time. In other words, dr dt. So we want to know what is that when, as we said above, dv dt is 100 cubic centimeters per second, and when the diameter is 50 centimeters. Now remember, the diameter is all the way across the sphere, but we don't have a variable for a diameter. We only have a variable for radius. So we're going to go ahead and convert the diameter of 50 centimeters into a radius of what? If you said 25 centimeters, that would be correct. Half of that diameter. So when dv dt is 100 cubic centimeters per second and r is 25 centimeters, which is half of 50. Okay, so that's our goal. Now, we have this dv dt, and we're trying to find dr dt. So we need a relationship between the rates at which the volume is changing with respect to time and the radius is changing with respect to time. And the equation that we want to start with then, that has the variable volume and the variable radius in it, is the one that relates the volume of the sphere or the balloon with the radius of the sphere or balloon. And that's just the equation for the volume of a sphere in general. So can you remember what the equation for the volume of a sphere is? If you said 4/3 pi r cubed, then that would be correct. 4/3 pi r cubed. Now we can take that equation that relates volume and radius and differentiate it with respect to time. That's going to introduce dv dt, the rate at which volume is changing with respect to time, and dr dt, the rate at which radius is changing with respect to time, and give us that relationship that we need between those two rates. So our next step is take the derivative on both sides with respect to time. Now on the left side, all we have is just dv dt. The rate at which volume is changing with respect to time is dv dt. And then the derivative of 4/3 pi r cubed with respect to t, well, the 4/3 pi, all of that's a constant coefficient, so that can come out of the derivative. So then the derivative narrows down into the derivative of r cubed with respect to t. Now r is changing as time changes, so you can think of r implicitly as a function of time, even though we don't explicitly know what that relationship is. And so we're going to think of r as being the inner function and the cubing function as being the outer function. So we're going to use a chain rule to take this derivative with respect to time. So this is going to be 4/3 pi, and I'm going to focus on the r cubed. So this is going to be 3r squared. This is the derivative of the outer function, leaving the inside part alone, leaving the r alone. And then times, by the chain rule, the derivative of that inner function with respect to time, the derivative of r with respect to time. So again, this is a chain rule happening right before our eyes. Now, if this said dr of 4/3 pi r cubed, then we wouldn't have any of this chain rule business going on. We would have r inside and then taking the derivative with respect to r. There's nothing really special going on there. You would just take the derivative as normal. But it's because the variable r and the variable t are different, that's when you know you have to use this chain rule. All right, so here we have an equation now that relates dv dt and dr dt. Now our goal, again, to remember, is to find dr dt. Let's take a moment to clean this up just a tiny little bit. So notice that the 3's cancel, and you've got dv dt is 4 pi r squared dr dt. Oop, I won't go down too far. So now we can solve for dr dt. Because that's the thing that we're looking for. And plug in now dv dt, which we know is 100 cubic centimeters per second, and r, which is 25 centimeters. So 100 and then 4 pi times 25 squared. And if you work that out and simplify, you end up with something like 1 over 25 pi. And then you got to think about the units. Again, the derivative, if you write it using Leibniz notation like this, like dr dt, then the units are going to be the units of r over the units of t. Now r is measured in centimeters, and t, it looks like, is represented in seconds. We got that from the dv dt. T is represented in seconds. So we have centimeters per second. One thing to notice is that because dr dt is positive 1 over 25 pi centimeters per second, that means that every second that passes, the radius is increasing by 1 over 25 pi centimeters, at least at this particular instant in time. Now, because it's positive, it's increasing. If you got a negative result for your derivative, that's okay. That just means that whatever that quantity is, it's decreasing with respect to time, or whatever you're taking it with respect to. That's something we're going to return to in some future packets as well, the increasing or decreasing that the derivative tells you about. All right, so that's it for this part. Thank you for watching, and see you next time.